Okay, folks, we're going to talk a little bit about friction, and to help us with this, I've got a graph here that's going to graph the amount of force I'm applying versus time, and I'll just go through that real quickly with you. So I'm going to collect some data. Right now I've got 0 newtons of applied force here. I'm not pulling, or you could call it the force of tension. I'm not pulling at all. And notice how exciting that graph is. You say, Mr. Bergeron, there's no graph, right? Because it's all 0 newtons. So if there's 0 newtons this way towards me, and there must be 0 newtons the other way as well. In other words, the friction between the felt pad and the block and the table must also be 0. Now I'm going to exert a small force, and I'll start at 0, but then I'll pull and exert a small force. So there's a small force, and I'm trying to keep it really steady. And so if we look at my value, I've kept a steady force of about 2 newtons, and this did not move at all. So because I was pulling with 2 newtons in this direction, and it was not accelerating, because it stayed in the same place, its velocity didn't change, there must also have been an equal force of 2 newtons in the other direction. So the friction in this direction must be equal to the applied force in this direction. Why? Because the acceleration was 0. Okay, let's take it, let's try the same thing again, but I'll pull harder this time until it starts to move, okay? And we're going to see something interesting there. So now I'm moving at a constant speed. Okay, what's the interesting thing that happened? Let's have a look at the spike here. We see that before it started to move, we got all the way up over 4 newtons. And then what I had to do was decrease the force right away so that I could move at a constant speed. So here I am moving at a constant speed with a force of 3 newtons. And what this tells us is there's 2 different types of friction. The first friction that we're interested in is the one that reaches a maximum right here. So when I'm pulling right before it starts to slip, okay, so when these 2 surfaces were not moving against each other, right before this started to slip, we reached the maximum possible, what we call static friction. And the maximum possible static friction, okay, is always going to be a little more than the other type of friction. This type of friction here, so it's about 3 newtons. This one was about, the maximum possible static friction was 4 newtons, and then what we call the kinetic friction was 3 newtons. Kinetic means movement, 3 newtons. This static friction, maximum possible static friction, is always more than the kinetic friction. So a couple of interesting thoughts there. So first off, there's 2 different types of friction to worry about. Static friction, when the surfaces are not moving against each other, that's called static friction. Static means not moving. Kinetic friction, when the 2 surfaces are sliding against each other. Now watch yourself, the surfaces have to be sliding against each other, because we'll talk about this some more later. Okay, so there's the 2 types of friction. Now, what affects this friction? Well, maybe how tightly the 2 surfaces are pressed against each other will affect this friction. How do we test that? Well, I'm going to run this again. I've removed the masses, so this is not being pushed down quite as hard. And let's see if I need more or less force to make this slide. Wow, that's almost nothing. Almost no force to make it move at a constant speed. So let's increase that. Let's put a little more and see what happens. Oh, this time we need a little more force. Okay, let's increase that again. So now they're pushing together even harder. So here, what do we have? We have a little over half a newton required to make it move at a constant speed. So now let's do it with, yeah, and we're getting maybe 1.1 1/3 newtons to get it to move at a constant speed as we increase the mass. We'll increase it one last time, and we'll see what that looks like. Yeah, and we have just over, just about 2.5 newtons required to make it move at a steady speed. So the kinetic friction keeps increasing as the surfaces are pushed against each other harder and harder. And in fact, if we do some careful measurement, we can determine that that relationship is actually linear, and that the greater the normal force between the two surfaces, the greater the force of friction will be, and it is what we call directly proportional. Double the normal force between the surfaces, you'll double the force of friction. Notice here we have the static friction, maximum static friction again, and then off as it starts to move, the total friction drops as we move at a constant speed. Okay, now there's something else that'll affect friction, and that's the nature of the surfaces. So this side was a felt pad, and this side was wood. Perhaps when we flip it over and we go wood on wood like this, we'll see a different value. So if you recall, for the felt on wood, we were somewhere around 4 newtons force required to move at a constant speed. So 4 newtons was the static friction. And now we're sliding at a constant speed with about 3 newtons. So we can see, if you look carefully, you see that it's about 3 newtons was required to slide at a constant speed along here. What if we put this wood, let's go with felt, on this really rough wood? And we'll see. Now this I won't be able to drag too far because I'm going to run out of room. But let's try the felt on that surface. And to keep things fair, I'll press the surfaces together as hard as they were. And now we'll see what happens. Wow. So it was way more than 10 newtons. I would need to switch this to a different setting. And that's not surprising. These surfaces will tend to grip each other really quite well because it's almost like Velcro. Now, what if I put the felt on top of felt? Well, we can make some guesses about whether that's going to have more friction or less friction. So let's give it a try. Oh, that's interesting. Look how it dropped off. That's because I was sliding off the edge. I don't know if I'll be able to do this one very well. Yeah, so we got a little period here where, we're getting about 8 newtons of kinetic friction as we pull this. So as you can see, there's friction depends on a few things. What does it depend on? It depends on whether the objects are sliding against each other. So if they're not sliding, you have static friction. If they are sliding, you have kinetic friction. So that's one thing. The other thing that it depends on is the nature of the surfaces. So certain surfaces will have a lot of friction between them. We saw that felt on felt was quite a bit of friction, right? We saw that the wood on the countertop was less friction. And we saw that the felt on top of this really rough wood gave us an extremely high amount of friction. And sometimes we want to increase friction, for example, with snow tires, and other times we want to reduce friction, for example, like in bearings of motors, where you have surfaces rubbing against each other. So that's our quick and dirty lesson on friction.